Right now, somewhere in the middle of the Pacific Ocean, a ship the size of a city block is being powered by something that looks like solidified asphalt. Not diesel, not petrol, not gas. A black tar-like substance so thick at room temperature you could stand on it. This is called heavy fuel oil, or HFO, and variations of this sludge power nearly 80% of global shipping by volume. We're talking about a fuel you've probably never heard of, a substance so viscous, so dirty, so difficult to burn that it requires its own heating system just to flow through a pipe. And yet, it moves almost 11 billion tons of cargo every single year. Your smartphones, your cars, your food across every ocean on Earth. Let's try and understand the world's most consequential and most controversial energy source, heavy fuel oil. To understand HFO, you need to start at a refinery. When crude oil is processed, it's heated and sorted by molecular weight. The light fractions rise. That's your gasoline, jet fuel, kerosene, and diesel. Valuable, relatively clean burning fuels. But at the bottom of the distillation column, literally, what remains is a thick black sludge. This is what's left after everything marketable has been extracted. It's the bottom of the barrel residue. Industrial waste that no one else wanted. At temperatures below 15 degrees Celsius, that's 59 degrees Fahrenheit, HFO turns practically solid. It's closer to asphalt than any fuel you'd put in a car. You could press your hand against it and it wouldn't move. It goes by many names: bunker C, number 6 fuel oil, IFO, intermediate fuel oil, or VLSFO, very low sulfur fuel oil. They're all variations of the same thing, the dregs of the oil refining process. For decades after the 1920s, refineries struggled to find uses for it. Then someone realised it could be burned in marine engines, and the entire global shipping industry reorganised around burning industrial waste. Here's the extraordinary part: just because HFO exists doesn't mean it should work as fuel. Getting it to burn requires a feat of industrial engineering. First, the fuel has to be heated. Ships carry enormous heating systems specifically to warm HFO to at least 50 degrees Celsius just so it can flow through the pipes. Otherwise it would just be a solid block. To actually burn the engines, it needs to reach 140 degrees Celsius. Ships are essentially floating fuel conditioning facilities before they're anything else. And the engines themselves are purpose-built for HFO. Typical marine 2-stroke slow-speed diesel engine stands 4 stories tall and weighs as much as dozens of main battle tanks. It runs at approximately 100 RPM. Compare that to car engines, which spin at 2000 to 6000 RPM under normal operation. The sheer physical scale and low rotation speed gives the thick, slow ignition fuel enough time to combust properly. The process of fueling the ship, called bunkering, involves specialised bunker barges that come alongside the vessel and port. They connect a high volume hose and pump hundreds or even thousands of tons of preheated HFO aboard over several hours. Here's the question everyone asks: if HFO is so complex to handle and this is harmful, why don't ships switch to regular diesel? The answer is straightforward: money. HFO costs roughly 30% less than cleaner fuel alternatives. For a single large container ship, switching from HFO to marine gas oil would cost an additional $60,000 to $80,000 per day in fuel alone, not per voyage, per day. Multiply that across a fleet of thousands of vessels running 365 days a year, and you're looking at tens of billions of dollars in additional annual fuel costs. Costs that would pass directly to consumers as higher prices on everything from electronics to food. HFO works precisely because it's a byproduct. Refineries produce it regardless. It's what's left when everything valuable is removed. Shipping companies found a buyer for what was essentially industrial waste, and built an entire global logistics network around burning it. By the 1960s, as refineries became more efficient and produced even larger quantities of residual oil, HFO cemented its dominance across ocean shipping. Today, the entire supply chain, from port infrastructure to engine manufacturing to bunker fleets, is built around it. Switching isn't just expensive, it's an infrastructure overhaul spanning thousands of ships, hundreds of ports, and decades of engineering investment. Now, historically, HFO contains sulfur at levels up to 35,000 parts per million for context. Road diesel in Europe is capped at just 10 parts per million. This results in global shipping generating roughly 8% of the world's sulfur dioxide emissions, more than all of the world's passenger cars combined. Studies estimate that these emissions contribute to approximately 400,000 premature deaths every year, mostly from cardiovascular and respiratory disease in coastal populations near major ports. Healthcare costs attributed to these problems cost an estimated $50 billion annually. And the particulate matter, the microscopic soot, is invisible but lethal. Black carbon from ships' exhausts doesn't just harm lungs. In Arctic regions, it settles on ice and snow, darkening the surface and accelerating melt. And when HFO spills, the damage is catastrophic in a way that no other fuel spill matches. In August 2020, the MV Wakashio, a Japanese-operated bulk carrier, ran aground on a coastal reef off Mauritius. The cause was almost absurd. Crew members had steered the 300-meter vessel towards the shore to pick up a cell phone signal for a birthday party. Over 1,000 tons of HFO poured onto one of the most biologically diverse marine ecosystems on the planet. The slick devastated coral reefs, wetlands, and protected coastlines. Recovery took years. Some sections may never fully recover. Unlike lighter petroleum products, HFO doesn't evaporate at ocean temperatures. It doesn't dissolve in cold water. It congeals and sinks to the bottom of the seabed and coats everything it touches. No technology currently exists to recover HFO from water columns once it is submerged. It also contains polycyclic aromatic hydrocarbons, PAHs, a class of compounds that are acutely toxic to marine life. Research has shown that PAHs from HFOs become significantly more toxic when exposed to ultraviolet light, meaning that a thin surface slick in sunlight can devastate fish larvae and coral at the water's surface even as the bulk sinks below. The shipping industry moves 90% of everything humans make and buy, and its fuel has been, for most of a century, one of the most ecologically dangerous substances in routine industrial use. The world has slowly been waking up to the HFO problem, but it's been a long sleep. In January 2020, the International Maritime Organization reduced the permitted sulfur content in marine fuel down to 0.5%, forcing ships to use low sulfur variants or install exhaust scrubbers. Furthermore, a July 2024 ban on HFO in Arctic waters finally came into force, though it still arrived with massive loopholes for double-hulled ships. Alternative fuels like LNG, methanol, and ammonia are coming in. There are also movements to build ships with SMRs or small modular reactors on board, meaning a ship like this could operate for around 30 years without need for refueling. But replacing a global infrastructure built on cheap sludge is a decades-long overhaul of a system that moves the world. So here's where we are. Right now, the fuel power in over 80% of global shipping is a substance so dense that you could pave a road with it. The world's most efficient mode of transport runs on the world's dirtiest fuel. And the race to change that without breaking the supply chains that feed and clothe and connect 8 billion people may be the most consequential engineering challenge of our lifetime.